Today we're going to talk about skeletal connective tissue, largely cartilage and bone. We want to look at the general organization of cartilage and bone. We want to look at the mechanism of growth, the mineral and organic constituents of cartilage and bone, and to look at the characteristic of the cells of cartilage and bone. Thank you. Connective tissue is composed of different components, and we talked about connective tissue proper, hematopoiesis, fat cells, mucous cells. But today we're going to talk about cartilage and bone, and that is your supporting connective tissue. Now, all these cells still come from bone marrow. Hematopoietic stem cells, you see there, give rise to all the white blood cells and red blood cells. And then also there's other cells. The monocyte gives rise to the osteoclasts, which is one of the cells that we are interested in today. It eats up cartilage and bone. Fibroblasts come here, and then they give rise to undifferentiated cells among the fibroblasts, and the connective tissue gives rise to the chondroblast, which gets trapped in its lacunae or space. It paints itself in a corner. When it gets trapped in its lacunae, now it's a chondrocyte, blast to site. Likewise, in bone, you have the osteoblast. Osteoblasts get trapped in their lacunae or space, and now they are osteocytes. So there's 5 types of cells. There's chondroblasts, chondrocytes in cartilage, and in bone, we have osteoblasts, osteocytes, and also osteoclasts, these macrophage-deriving cells that eat up bone. Now, the function of cartilage is, in the embryo, it is our skeleton. And here you can see that we have a skeleton of cartilage. And then it develops and is remodeled into bone. And in fact, you continue to have this remodeling in adolescence until you get the total height of the individual. So cartilage is flexible support. Here we see it in the trachea. Here we see it in joints. Here, cartilage. This is hyaline cartilage in both cases. And it returns to the original shape in some types. In the ear, that would be the elastic cartilage. In the nose and respiratory tract, we have the different types of cartilage. Now, cartilage slides over one another. So this is cartilage, this is bone, this is cartilage and bone. It's on the articular surfaces, as you can see. And its cushion, its cartilage has limited compressibility, is what it has there. And so it can compress a little bit. Also, it has no nerves. So no pain with cartilage. The pain you get in your knees is really the pain you get from the bones, not from the cartilage itself. And here we can see in our kneecap, we have cartilage at the end of bones. Here and here, we also have cartilage at the end of our ribs as well. Now, in terms of organization of cartilage, you most always, in 2 of the 3 types of cartilage, you have a perichondrium, near chondrium. And that's dense, irregular connective tissue like all capsules of the world. And you can see it on either side. This is epithelium and connective tissue, but here's the perichondrium here and here. Just inside the perichondrium, you have the osteoblast, the chondroblast giving rise to cartilage. And then trapped inside in a lacunae would be the chondrocytes. So this cell gets trapped and it becomes a chondrocyte. It forms the interfaces of cartilage and bone, is a supportive tissue, harbors blood vessels. All that is a perichondrium. So the perichondrium supports the cartilage. It has the blood vessels because there's no blood vessels inside of cartilage itself. Now, cartilage is mostly type 2 collagen. It lacks the obvious periodicity. It does have a little bit, but it's not obvious. And it's sulfated proteoglycan. So you have congruent sulfate, keratin sulfate, and that's what makes cartilage blue with the H&E preparation. It's capable of holding water. In fact, nutrients can diffuse through it, so it's diffusible. It's avascular. It gets the nutrients waste from exchange from the perichondrium. So it doesn't have blood vessels inside there, and as a consequence, you don't have precursor cells to heal it. Type 2 collagen, here we see hyaluronic acid and the type 2 collagen in through there and there. As we can see, more type 2 collagen interacting with the proteins with the hyaluronic acid core. And here you would have the congruent sulfates coming off these proteins. So here we see some chondrocytes that are trapped in their lacunae. Perichondrium, this would be periosteum next to the bone. So here we can see the perichondrium, which is a pink thing that we see in here. We can see electron microscopic view that has some fibroblast-like cells, and these transform into chondroblast. And the chondroblast gets trapped in its lacunae, and that becomes a chondrocytes. And so here we see chondrocytes in through there, trapped in their space, lacunae. And in between there, of course, you have the matrix. And the matrix, hyaluronic acid, type 2 collagen, congruent sulfates, and all making cartilage blue with H&E preparation. Here you see chondrocytes. Chondrocytes in through there. Amino acids come in. They get protein synthesis in the Refiar, Golgi, and secretory collagen as pro-collagen, and collagen is produced in this case. And so it will be making type 2 collagen. Sugar and sulfur comes in through the Golgi and is added to it, and that makes the extracellular matrix bluish tint with all the sulfates. So the proteoglycans and collagen is what we have. Type 2 collagen is what it is. And so as you see again, here's a type 2 collagen bundles here fibers here and here, hyaluronic acid, congruent sulfate, as we saw before. So there's three types of cartilage. You have the hyaline cartilage, which is what we have in our trachea. That's what we had at the end of our ribs. We have fibrocartilage, which is where tendons and ligaments attach to bone. And so this is type 1 collagen with a little bit of type 2 collagen right around the individual cells. Elastic cartilage is very much like hyaline cartilage, except it has a high density of elastic tissue inside there. We start with hyaline cartilage. That's what's in our trachea. We see the perichondrium on either side, here and here and here. And then we see the cartilage inside there. This is epithelium of the surface and glands inside the respiratory tract. Elastic cartilage, you have elastic tissue in through there, and usually you only have doubles, two cells in a little space. In the case of hyaline cartilage, you can have multiple ones, up to 8 or so. And so these are isogenic groups, and these isogenic groups all are given rise from a single cell dividing by mitosis or interstitial growth. But in elastic cartilage, you just have a couple. You don't have so many in number. The outer layer of the ear, we can see the ear. There's epithelium on either side here and there. And then this is elastic cartilage, and you can see the elastic fibers in there around in the in the space between extracellular space between the cells, and that's the ear, is that we're seeing. So you have skin on either side. Here again, we can see it. This is in a cat, and we can see the chondrocytes, the chondroblasts on the edge, and we can see elastic fibers in there, and this is the perichondrium, and they're pulled apart, but it's there. Now, fibrocartilage is where you have a tendon or ligament attaching to the bone. So here's the bone, there's a tendon or ligament. Right at the surface of the bone, these otherwise look like fibroblast cells give rise to chondrocytes. And here you can see they're trapped in their little lacunae themselves. Here you see the chondrocytes trapped in their lacunae. There's no perichondrium because each of the groups of cells are in dense irregular connective tissue. That's what a tendon is made of and ligament is made of. And so you don't need an extra capsule because each group of cell is already and essentially a capsule. So here we see type 1 collagen in fibrocartilage because it's mostly a tendon or ligament, and the fibroblasts have made the type 1 collagen. However, right around each one of the chondrocytes will be type 2 collagen located right around each one of those. Here we see it in a fetal elbow, right in there where this tendon is going to attach to this bone. You can see these cells here. You can see them hierogmatic, these each in their lacunae. These are the chondrocytes of the fibrocartilage that you can see. There's type 1 collagen in between. These big bundles here are type 1 collagen. But around each one of these, you can have type 2 collagen. And here we can see a nice illustration. Remember the tendon coming in, cigar-shaped cells, look like basketballs here, and there's the bone in through there. You have the same thing here in this cat, right in this region right there, where you have the fibroblasts in the tendon, and all of a sudden you have the chondrocytes located in their lacunae as you approach the connection to the bone. Hyaline cartilage, we see isogenic groups, as I mentioned to you, glassy shape. Sulfur makes it blue with H&E preparation, and it's at the end of bones. We see those. You see that kid sucking the bone. It's glassy, has gags. It's a temporary skeleton of us, and also it's the articular surfaces of bones in the adults. And also, cartilage, hyaline cartilage, is involved in the growth of long bone, and it does it at the epiphyseal plate. And so, a bone cannot grow from within; it can only grow from the sides. And as a consequence, it recruits cartilage, which has interstitial growth, to increase the length of the bone, and then it's remodeled from cartilage to bone, and that's what happens. So you have cartilage in through there, dividing, making this bone longer, and then all this cartilage eventually is replaced by bone, except you still have some on the articular surfaces. And here we can see of the epiphyseal plate the different zones. You have the zone of reserve or resting cartilage. You have zone of proliferation where the cells are dividing by mitosis. Zone of hypertrophy, and this is what actually extends this thing, is that these cells increase in size as they mature, and then the zone of calcification. So when the cartilage is calcified, no longer is it diffusible. Nutrients can go through here, but they can't go through there, and that kills the chondrocytes. And then the osteoclast comes in and destroys these cells, and it's remodeled as bone. And here we can see the articular surfaces and how the collagen actually runs kind of like this and makes kind of scaffolding so it can resist pressure. And the only place that you don't have a pericardium of hyaline cartilage is the articular surfaces because it would be worn off. But it is still within the synovial membrane. And so you have synovial fluid in through the hyaluronic acid in through there, makes it slick. You'd have so you have fluid inside there, and it's essentially in a capsule, even though there's a little space there. Attach the sternum to the ribs, right in through there. We have it. This is cartilage in through there. Thanks to Body World for us to show that. And then also the cartilage in the respiratory tract, not only in the trachea but also in the bronchus. So the difference in bronchus and bronchioles is whether you have cartilage or not. So there's centers of chondrification. That is, other cells look like fibroblasts, divide, they differentiate, and then make chondrocytes, and then the chondrocytes divide to produce other chondrocytes. This is interstitial growth. So you ingrowth from within, where one cell gives rise to other ones, and in the case of hyaline cartilage, you have multiple groups. In the case of elastic cartilage, you just have mostly doubles. And here we can see interstitial growth. The cell membrane is separating this cell from that cell. And this phenomenon here is what's going on right up there where you have interstitial growth, proliferation of the chondrocytes. Appositional growth is where you grow from differentiation of fibroblasts like mesenchymal cells that give rise to chondroblasts, which then differentiate into chondrocytes. So this is appositional growth on the sides, and that's how you increase in width. And so here's a perichondrium, as we talked about before, which is right in through there, and then these guys differentiate to form chondrocytes from chondroblasts that came from progenitor cells that's in the perichondrium. So in summary, cartilage, we have hyaline cartilage, elastic cartilage, and fibrocartilage is what we have. And here we can see, as we said before, you have protein production. The collagen, procollagen, is produced by these, and you have amino acids coming in. Sulfur and sugar comes in to put the sulfated gags that are in there, and these three cells, 5 cells, the osteoclasts, osteocyte, osteoblast, chondroblast, chondrocytes, these 5 cells all come from the bone marrow, from undifferentiated cells, stem cells in the bone marrow. So those for cartilage and those for bone, and cartilage and bone are connective tissue. And if we look at bone, we can see it protects our exposure. Protective, it's an enclosure, closes our brain, protects our brain, and also protects hematopoiesis inside of long bones. And here we can see our bones here. Bone allows us to stand up. Now, the function of bone, in addition to skeletal component, it also has to do with calcium regulation. Calcium regulation is very important for muscle contraction. And parathyroid hormone causes bone reabsorption. And calcitonin prevents reabsorption. These hormones work together to regulate free calcium level. Every minute, 1/4 of the free calcium level is exchanged, either stored or released. Hematopoiesis, here we see the host of cells in through there need to be protected in bone, and also this is a source of the undifferentiated bone cells, the precursor cells to the bone cells. Now, in terms of the cell types in bone, the osteoblast secretes osteoid. Osteoid is the extracellular matrix of bone. It expands the bone expands by appositional growth. It cannot have interstitial growth, only by appositional growth. So you get the osteoblast here produces osteoid until it traps itself, traps the osteoblast in a lacunae, and that is an osteocyte. So osteocyte is the osteoblast that's trapped in the bone matrix. So we have osteoclast that eats bone, osteoblast that lays down bone, and osteocyte are the cells that are in the lacunae themselves. Mesenchymal cells, we have the mesenchymal cells here that will differentiate into the osteoblasts that we see there. So the different cells, the osteoblast lays down bone, osteocyte is what's trapped in the matrix, and in the matrix you can see there's a mineral deposit, and that's what makes. So it's type 1 collagen, and we can see the periodicity there very distinctly in type 1 collagen is the extracellular matrix, and then that's mineralized, and you can see the hydroxyapatite darkness there. Now, in the bones cells, we have the osteoclast, which is a multicellular, multinucleated cell with a ruffled border on one side, and this ruffled border is contacting the bone. And that ruffled border helps the osteoclast have an environment here. So it puts in citrate, it lowers the pH so it can dissolve the bone. So this is a phagocytic cell, come from a monocyte as well as other macrophages do. So here we see it, osteoclast. It comes from the monocyte, which ultimately came from the bone marrow. Osteoclasts eats wholes. That's what they do. Multi-nucleated cells. You can see one there, and you can see these little places that they have dissolved the bone. So osteoclast has a ruffled border. There's one of the nuclei of several nuclei, and we see the ruffled border, and this is where bone is being reabsorbed. So little vesicles are transporting enzymes there that could digest the bone. And of course, there's type 1 collagen in the bone, and then there's also hydroxyapatite crystals. Ruffled border is very important. So here we can see again, this is the ruffled border on the part of the osteoclast that contacts the bone. Also, osteoclast can break down cartilage too. If it can break down bone, it can certainly break down cartilage, and that's what it does sometimes. So sometimes this is cartilage here on this side of that ruffled border. So there's two hormones that regulate it. As we said before, parathyroid hormone stimulates osteoclast production. So you produce more osteoclasts, and that makes bones more porous, frees up calcium. Calcitonin removes the osteoclast ruffled border. Okay, so if you remove the ruffled border, you eliminate the environment that allows digestion to occur, reabsorption to occur, and as a consequence, you lower blood calcium levels by having less action of the osteoclast. Remember that 1/4 of the free calcium in the blood is exchanged every minute. So there's a tight control here to maintain calcium levels in the body. So here we see the osteocyte, which is located in its lacunae, osteoblast located on the side, and here's a multinucleated osteoclast. Here we can see bone in through there with the calcium carbonate matrix. So osteoid, which is what's secreted by the osteoblast, is a mixture of type 1 collagen, and it has affinity for nucleation sites for hydroxyapatite, which is a calcium phosphate. So calcium phosphate is hydroxyapatite, the darkness that we see there in the bone, and the osteoid produced by the osteoblast and osteocytes with the type 1 collagen, it's a nucleation site for precipitation to occur. So this would be floating around and it precipitates in bone. So if you look at the extracellular matrix, this is the bone, this is the osteoblast here laying down bone, is polarized. It adds it here first, which is next to the present bone, and then it continues to produce it all the way around itself, so it is trapped in its lacunae, like osteoblast, osteocyte that we see there. Calcification adds a firmness to the bone. But in doing so, it also prevents the fusibility of the matrix. So the bone has to come up with another way to get nutrients between cells. And it done that by you have the lacunae attached to one another by these canaliculi. So these are canaliculi. It's really where the cell already was and touched the adjacent cells, and then the matrix was put in around it, and that space where the cell was is now a little channel, canaliculi that we see there. And that's how nutrients get from the endosteum here and here and here. It gets in through there, and it migrates from cell to cell to cell, and they pass the nutrients through with the gap junctions. So you have gap junctions located in these canaliculi that facilitates the nutrients coming from the bloodstream into to the cells that are inside. Their bone has living cells. They're not dead. They're living, and it's the canaliculi that allows it to override the fact that bone is non-diffusible. Now, you don't have canaliculi in cartilage because the cartilage is diffusible. Nutrients can diffuse through, but they can't in bone. Now here we have a compact bone is what's on the outside of bone in through there, and it's remodeled differently than the spongy bone or the cancellous bone. So spongy bone and cancellous bone is the same thing, and in between there is where you would have the cells of the bone marrow. So this is compact bone here. So here we see a diagram of compact bone, and what we see is there's a periosteum on the outside, osteum on the inside. Also, the Haversian systems itself have osteum inside there as well. And so from appositional growth from on the outside, we have these layers here, which are circumferential lamellae. You have an outer one and an inner circumferential lamellae of the bone. And then you have these osteons or Haversian systems that run down the length of bone. Blood vessels come in. You have the Volkmann's canal, which then runs perpendicular to the Haversian canal. So we have these Haversian systems. We'll talk about them. You can see one right here, and the Haversian canal is what's on the inside. So Haversian system is a remodeled unit of compact bone that we can see. So we have circumferential lamellae, as I mentioned, from the periosteum and from the osteum. It could be outer circumferential, and you have an inner circumferential, and that adds width to the bone, appositional growth. No interstitial growth in bone because it can't push it apart. So we have osteum inside a compact bone. Also, it's inside the Haversian systems as well. So we have periosteum on the outside, osteum on the inside. So if we look at one of those Haversian systems, you can see the Volkmann's canal, the Haversian canal here and here, and you can see the lacunae or the space. What we're seeing here is the space is dark, and then you can see little channels. Those are the canaliculi that are in there, and so this is one Haversian system, which is one of these units here. From there to there is one unit. From there to there is another unit, and it runs down the length of bone. So here we can see there it has in there these cells that are in the lacunae, of course, are going to be the osteocytes. The ones that are developing inside the osteum are going to be osteoblasts. So here we can see these, and you can see the little canaliculi which connects these cells with those cells, and they have gap junctions in there to provide nutrients from coming through. So in compact bone, you can see that you have osteoclasts get together, dig a hole, and they're digging a hole. Osteoblast from the osteum just fills in, differentiates from these mesenchymal cells here that fills in through there, and then finally it seals this as a osteon or Haversian system, and this is the remodeling that we can see. So in terms of remodeling, you have osteoclasts dig a hole, osteoblasts dig it in from the osteum, and then they close up the space. So the osteon is developed just the opposite of a tree. It's from outside in. A tree adds to the outside. This adds to the inside, is the way it is. So in the remodeling of bone, the osteoclast will eat a channel through there, and that's the size of this osteon that's replaced. And so in between there, sometimes you may have interstitial lamellae, that is lamellae that was not a concentric with the last Haversian system, so it's in between. So there's varying ages of these. Sometimes it eats a new one, sometimes it leaves an old one, and the old one is interstitial lamellae. And so here it kind of shows you what's happening. You have the osteoclasts here with the cutting comb. They're cutting the channel, and they're the one that's directed. These other guys just fill in where the hole is. If the hole was curved, they would fill in a curved hole. But since these guys eat in a straight line, then it fills it in a straight line. And so this is the A reabsorption cavity is already made the hole all the way around. Osteoclasts are right inside here. And then the osteoblasts are laying down bone. And finally, it's already complete. And so these guys here are nearer than those there because it adds to the inside, as I mentioned to you. So a cross-section of this will be a complete Haversian system. This will be an incomplete one. It hasn't closed in all the way, and this would be one that's just been open. And then this is an opening one that we see there. So it's the same thing as what we saw here, where you have osteoclasts digging the channel, and then osteoblasts laying down bone, getting trapped in there, and become osteocytes. And so we can see where new bone is developing. Osteoclasts is eating up whole. These are osteocytes in through there with lacunae, in their lacunae, and the canaliculi connected from one another. And here we can see the remodeling process. The interstitial lamellae is what was laid down by appositional growth from the very beginning, and it didn't always, they don't coordinate these things to have them close one another. And here you can see where the remodeling ate some of this but didn't eat the interstitial. And here we see the third remodeling where you had this one and then that one and then this one on top of that. And so it dug a hole and it ate some of the interstitial, some of the first one, some of the second one, and you got the third one remaining. So it's not just a perfect circle on top of the other perfect circle. It'll eat whatever it contacts in the third generation of the process. Now, there is some directionality of this thing, and this is due to a piezoelectrical field, which whenever you compress crystals, calcium crystals and other crystals as well, it directs the osteoclast, because when crystals are compressed, they give off electrical charge. And so where your weight is down is compressing the crystals, not only calcium, but other crystals too. And in doing so, it gives off electrical charge. And it's that electrical charge that directs the osteoclast to come down the length of the bone. That's why these Haversian systems run down the length of the bone and not to the right and left, because the weight is at the bottom of the bone, or maybe is wherever the weight bearing is. That's the effect that it has. A piezoelectrical field causes compression of minerals, directs osteoclast down the length of bone because it gives off electrical charge, and that electrical charge is what directs the osteoclast, which digs a hole. Osteoblast just fills in. They're not directed. If there's a hole, it fills it in. If it's curved, they curve. But it's not curved because it's straight, because the osteoclast made it straight. So in the remodeling process, you can see here, you can see the remodeling has occurred here. Each one of these is an osteon or Haversian system with a Haversian canal, osteocytes in through there, periosteum, inosteum on the inside. And there is intermembranous ossification, that is, without a cartilage core. Intermembranous, we call that. So you have mesenchymal cells that give rise directly to osteoblast. So osteoblast lays down bone and makes a matrix. The osteon gets trapped in this matrix and it becomes an osteocyte, just like before. And then you'll have macrophages all around. The osteoclast will move into the chest to remodel that. Intermembranous ossification. And where you have that is in your skull, and sometimes in the vertebrae, flat bones, is you have intermembranous ossification. There's also endochondral ossification. This is the one that we've talked about so far, where you have cartilage develop, and then you get calcification of that, and as a consequence, the cells die, and it's remodeled with bone. And here you can see some primary spongiosum, where you have bone on the outside and cartilage is not completely filled in. So this is located right in that little boy's finger there. And here we can see endochondral ossification, where this was a cartilage at one time, and now you have cartilage only on the end of it. So this is cartilage. This is perichondrium in through here, chondroblast right through there, and a sulfonated extracellular matrix that gives it its blue scent. And we have the the chondrocytes located in this cartilage. They're trapped in their lacunae. So endochondral ossification during the bone formation, when you're an embryo, your skeleton was all cartilage, and then it's replaced with bone. So you have the primary ossification as your diaphysis, and then you have a secondary ossification. That's your epiphysis, as you see here and here. So this is a primary one, and then this is a secondary one. And the more complex the shape of the bone is, the more you might have of these secondary centers of ossification. And here you see you have multiple ones here on some of your vertebrae. So in terms of endochondral bone growth, in width, you have expansion of the compact bone by appositional growth. That is, on the edge of bone, or the periosteum or the endosteum, you have differentiation of fibroblast-like progenitor cells, mesenchymal cells. They go to osteoblast, and the osteoblast changes to osteocytes whenever it gets trapped in lacunae. But in terms of length, since there's no appositional growth, it has to engage the epiphyseal plate. And the epiphyseal plate is cartilage that we see there. And you get cartilage growth because it can have interstitial growth. It can grow from within. And then it's replaced by bone. And that's where you get primary spongiosum, where you have a cartilage core, or secondary spongiosum, which is totally bone that has been replaced all the cartilage that we see there. And here we see how the shapes of bone changes as the individual grows. And so you have to remove the old bone to allow this modification to occur. And here we can see where cartilage is located and where the epiphyseal plates would be located. Now, in terms of bone repair, it's very similar to the histogenesis of bone. That is, you break, you get a blood, you get a clot there occurring, and then you have cartilage. Cartilage replaces the broken bone, just like endochondral ossification occurs. And then the cartilage becomes calcified, and so the bone heals quickly, but the cartilage is not stout. That's why you still have to have a cast on until the cartilage is remodeled as bone. And so it can remodel there, and you can't even tell where the thing was. And so in terms of repair of bone, it tries to straighten it out. There's some forces that are involved there. When you got more compression here, less there, you get more growth there, it pulls it there together. It tries to straighten it out. But of course, we have a cast to keep it straight too. So the function of cartilage in bone, in the embryo, your early bones were cartilage, and then they're replaced. In the adult, you have the articular surfaces of bone, you have cartilage. So to support land animals, for support enclosures like your brain and hematopoiesis, you need bone. So in final summary, cartilage and bone, cartilage was in the embryo. Cartilage slides over surfaces. It holds weight. It doesn't have slip and slimy, so that the bones won't touch one another, and it's compressible. Bone provides for our enclosures. It provides support of a statue, and it supports hematopoiesis. And also, bones, when bones growing, it benefits from cartilage. It grows in length by soliciting cartilage to divide by interstitial growth, which bone cannot do, and then it replaces the cartilage with bone. And these, we can see the different ones: the zone of reserve, proliferation, hypertrophy, the increase in size and calcification, and it's remodeled as bone. Bone is non-diffusible, therefore it has to have an elaborate system to be able to get nutrients from one cell to another cell, and they have it through these canaliculi. We want to thank the various books that from which we took some figures from. Those books are the source of those, not me, and so I don't want to take credit for any of those diagrams that came from the book, and we thank those books for those presentations. We also thank Body World for their presentation, for their images as well. Next time we're going to talk about muscle, or go to the Museum of Natural History. Here we see the Iceman. Here we can see the subway train coming through Washington at D.C., and we can see the Capitol there, Museum of Natural History there. This was the Library of Congress, right behind the Capitol that we were able to see. If this information was useful, please share it with your colleague. Thank you.